Hi class, I am Damika Musi from Rhodes College. In this video, I am going to discuss the importance of significant figures and the precise data in problem solving. I will carry out a simple experiment to determine the densities of regular Coke and Diet Coke. Here I have the samples of Coke and Diet Coke, both degassed by stirring overnight. This is the Diet Coke and this is the regular Coke. So what do you think? Do these samples have the same density? I think that their densities are different because regular Coke has sugar in it and Diet Coke has very small amount of artificial sweetener in it. Our hypothesis is that the density of Diet Coke is lower than the density of regular Coke. You know that density is mass per unit volume. I will use 25 milliliter of each solution and measure its mass using an analytical balance. I will measure the volumes using two different methods. In method 1, I will measure the volumes of each sample using a 100 milliliter measuring cylinder. This is the 100 milliliter measuring cylinder, and remember we can measure the volume to 1/10 of a milliliter using this measuring cylinder. In method 2, I will measure the volumes using a 25 milliliter volumetric pipette. This is a 25 milliliter transfer pipette that delivers 25.00 milliliters at 20 degrees centigrade. Using each method, I will analyze multiple samples from each solution and we can determine the average densities for regular Coke and Diet Coke solutions. We will have two sets of density data determined by method 1 and method 2, and we can see which method helps us to test our hypothesis unambiguously. I will use this white plastic bottle to measure the mass of Coke, and I will use the measuring cylinder to measure the volume of Coke. First, I will measure the mass of this bottle. It will be the initial mass. I will transfer 25 milliliter of Coke from the graduated cylinder into the plastic bottle and measure the final mass. The final mass minus initial mass is the mass of Coke. We will know the volume and the mass of Coke and we can calculate the density of Coke. Now let us carry out this plan. This is the mass of the empty bottle or the initial mass. We measured the mass of this white plastic bottle, and now I am going to pour 25 milliliter of this Diet Coke into this measuring cylinder, and then I am going to pour that Diet Coke into the white plastic bottle. I will try to slowly pour the Diet Coke along the side of the measuring cylinder so that I can avoid any air bubbles. It is about 20 milliliters. The rest I am going to add using this Pasteur pipette. I'm trying to keep my eyes at the level of the meniscus. Alright, now it is 25.0 milliliters. Now I am going to pour every drop of this Diet Coke into this plastic bottle. As you know, measuring cylinder is not designed to deliver volumes precisely and accurately. That there are some droplets of Diet Coke still left inside the cylinder. Now I am going to take the mass of this bottle with Diet Coke. This is the final mass, the mass of the bottle with Diet Coke. Here I calculated the density of Diet Coke using our first mass and volume data set. Mass of Diet Coke is 24.2 0.2859 grams obtained by subtracting the mass of the empty bottle from the mass of the bottle with the Diet Coke. Volume of the Diet Coke is 25.0 milliliters. We have only 3 significant figures for the volume because we used the measuring cylinder to measure the volume. Density is mass divided by volume. So the density is 0.971 grams per milliliter. We have only 3 significant figures for the density because we know that in division and multiplication, the number of significant figures in the result is set by the original measurement that has the smallest number of significant figures. In this case, the volume has the smallest number of significant figures. Now I will repeat this process with 4 more samples of Diet Coke to determine the average density of Diet Coke using the method 1. I gathered this data using the method 1. In method 1, the volume of soda was measured using the 100 milliliter measuring cylinder, and this is the data I gathered for Diet Coke. Gathered 5 replicate measurements. This is the final mass, this is the initial mass, this is the mass of Diet Coke determined by final mass minus initial mass. This is the volume measured using the measuring cylinder, and the density is calculated using the mass and volume measurements. And this is the mean of these 5 replicate measurements. The standard deviation is 0.02. As you see here, the first non-zero digit of the standard deviation is at the second decimal place. Therefore, the last significant figure of the mean should be at the second decimal place. So the mean was rounded up to 2 significant figures. You also know that the experimental true value is a range defined by the mean and the standard deviation. According to method 1, this range for Diet Coke is 0.95 to 0.99. I also collected the data for regular Coke using method 1. The mean is 1.00 grams per milliliter. The standard deviation is 0.03 grams per milliliter. The range of the mean plus or minus standard deviation is 0.97 to 1.03 grams per milliliter. Now, let us look at our hypothesis. The density of Diet Coke is lower than the density of regular Coke. That is what we were testing. If we just look at the mean, then the mean of the Diet Coke is slightly lower than the mean of the regular Coke. However, we have a standard deviation that we cannot disregard. That tells us that the true experimental value is a range of the mean plus or minus standard deviation. If we look at the range, the lower end density values for regular Coke overlaps with the higher end density values of Diet Coke. Therefore, we are unable to test the hypothesis unambiguously using this data because the data have low precision. In other words, they are scattered. Our data suggests that the low precision is mainly due to the volume measurements. Therefore, in method 2, we will measure the volumes accurately and precisely using a 25 milliliter transfer pipette. Hi class, now I am going to show you how to use the pipette. This is a 25 milliliter volumetric pipette. Here I have some deionized water with which I will rinse the pipette. I also have a waste beaker here. Let me show you how to clean the pipette first. This is the pipette bulb. I am drawing DI water into the pipette. Now I have enough water inside the pipette. Now I roll the pipette by the ends of the pipette, and now I am draining the water into the waste beaker. Usually draining is faster if we do it along the sides of the beaker. Next I am going to rinse the pipette with the test solution. I will use the same tip rolling method to rinse the pipette with the test solution. Now my pipette is all conditioned. I am ready to pipette the test solution. I am immersing the pipette in the test solution or the Diet Coke solution. Make sure that the pipette stays straight in the solution. Now I am going to adjust the meniscus. The bottom of the meniscus is at the 25 ml marking of the pipette. Now I am transferring the liquid into this plastic bottle. Remember to keep the pipette straight. You can tilt the bottle a little so that the liquid will drain along the side of the bottle. Now almost all the liquid has been transferred into the plastic bottle. We want to be a little patient here to make sure everything is transferred into the bottle. Now you will see that there is a little bit of liquid trapped at the tip of the pipette, and it's okay. We do not want to try to get that liquid into the bottle because the pipette is calibrated to retain that small amount of liquid at the tip of the pipette after delivering 25 milliliter of liquid. We gathered these data for Diet Coke using the method 2. In method 2, we measured the volume using a 25 milliliter volumetric pipette. So we were able to obtain 4 significant figures for the volume of soda. Therefore, density was also determined to 4 significant figures. The mean density for Diet Coke is 0.9971 grams per milliliter. The standard deviation is 0.0003 grams per milliliter. This is a very small standard deviation. Now we have a very tight range for our experimental true value, which is 0.9968 to 0.9974 grams per milliliter. Here is the data set for regular Coke. The mean density is 1.039 grams per milliliter and the standard deviation is very small, that is 0.0003 grams per milliliter. Although the first non-zero digit of the standard deviation is at the 4th decimal place, we have to round off the mean at the 3rd decimal place to have 4 significant figures because our volume data has only 4 significant figures. So the matching standard deviation for this mean is 0.000. This is good news because our values are very precise. Since there are no indication of systematic errors, we can consider that these data are precise and accurate. When we compare the experimental densities of Diet Coke and the regular Coke, we see a clear difference. The density values do not overlap like the values obtained using the method 1. We can clearly conclude that the density of Diet Coke is lower than the density of regular Coke. This clear understanding is possible only because we obtain the high precision volume data using the 25 ml volumetric pipette. I hope that this exercise will show you the important role of significant figures in experimental data. In the absence of systematic errors, the higher number of significant figures in your data will lead you to a clear understanding of what you investigate. That is why we use expensive volumetric glassware and other quantitative equipments like analytical balances. When the experiment is linked to decision making, the data with high precision and accuracy will help you to make a better decision.